Welcome to my channel GATEquestionsECE. Let's begin with this question having question code 102. So this is part 2 of this question and we will calculate the Pmf of Z1, which is maximum of X1 and X2. So the Pmf of this can be calculated in two ways by using two methods. One is Pmf or PDF method and other is CDF method. So guys, I have already made the part 1 of this video, which you can check in this I button. In the part 1 I discussed that we can find out the PMF of this function by breaking the whole 2D of x1 and x2 into three regions. First one was region 1, which is case 1, x1 greater than x2. Second region, x2 greater than x1. And third region is x1 is equal to x2, which is this straight line. So for each of this region, we calculate PMF of Z1. In case 1, Z1 will be equal to x1. In case 2, Z1 will be equal to x2. And in case 3, Z1 will be equal to x1 or x2. So we find out the PMFs of each of these cases, and after finding the PMF of Z1 in each of these cases, we sum this up. We sum all the PMFs and find the overall PMF of Z1. So that was the PMF method. So now we will discuss CDF method, in which we will use the joint CDF of X1 and X2 to find out X1 and X2 to find out the CDF of Z1. And after calculating the CDF of Z1, from the CDF of Z1, we will calculate the PMF of Z1. So before going to CDF method directly, I would first like to explain what is the CDF itself. So let's see what is the CDF. To explain what is the CDF, I have already drawn a diagram over here, which I will be using in this explanation. For a single random variable, CDF is represented by this capital subscript X. If X is a random variable, we denote, let's say X1 is a random variable. Then we denote it with capital F for some sample value x1. It is equal to probability that x1 is less than equal to some sample value x1. Let's say this x1 sample value is this value. So this red line will be x1 is equal to x1 line. So according to this formula, graphically we can see, so we can say that this probability is the probability that random variable x1 lies to the left of this line or on this line. So this defines a region. What is that region? That region I will be drawing here. So this region includes the region to the left of x1 is equal to x1 line, and also includes this line itself. Okay, so that is the meaning of probability of CDF. Similarly, we can define the CDF for x2 for sample value x2. This will be equal to probability that x2 is less than equal to some sample value x2. So let's say this value is x2. On x2 axis, let's say this value is small x2. So this line, this blue line will be the straight line x2, capital X2 is equal to small x2. So according to this definition, we can see, if we see what is the region that is defined by this, so it is saying that random variable x2 is smaller than or equal to small x2. The region defined by this equation will be the region which I am going to draw now. So this region which I have drawn with blue lines, including this straight line x2 is equal to x2, this equation defines this region. So random variable x2 can lie anywhere in this region according to this, and the probability that random variable capital X2 lies in this region which I have drawn with blue lines is the CDF of capital X2. Similarly, we can define joint CDF of X1 and X2, which is we denote by capital F X1, comma X2 with sample values X1, comma X2. It is the probability that X1 is less than equal to small x1, and for and we use intersection. There is another representation of this which is usually used in books. It is written like this. In place of and they write comma, just for simplification of writing it. So if I write this x1, capital X1 less than equal to small x1 as A and this as B, so A intersection B, which means the region that is common to both A and B. We can see the region that is common to both A and B will be the region that has cross lines, that has both blue and red lines. So I am going to draw here that common region with yellow lines. So the joint CDF of X1 and X2 is nothing but the probability that X1 X2 lies in this region, which is common to region A, which is drawn here with red lines, and region B, which is drawn with blue lines. There is one more point that I will like to tell you. You note down very carefully that this region has one corner point. That corner point is this point. And you note down very carefully that coordinates of this corner will be x1, comma x2. So depending upon the values of x1 and x2, this corner can lie above this line, like I have drawn in this case. Here I have assumed, while drawing this diagram, I have assumed that x2 is greater than x1. So for example, x2 can be 2 and x1 can be 1. In such cases, this corner of this region of our interest will lie above this x1 is equal to x2 line. There can be another case in which x1 is greater than x2. For example, x2 can be 2 and x1 can be 1. In that case, this corner of the region of our interest will lie below this x1 is equal to x2 line, and it will look like this. In that case, the region of our interest will look like, suppose this is x1 is equal to x2 line. In that case, the region of our interest will look like this. So this will be the region of our interest. This will be the region of joint CDF that I am talking about, because here x1 will be 2 and x1 will be 1. So the corner will lie below this line. And there can be third case where x1 is equal to x2. In that case, for example, x1 can be 1 and x2 can be 1. In that case, suppose this is x1 is equal to x2 line. In that case, the region will have corners exactly lying on this line depending on the value of x1 is equal to x2. Suppose it is 1 1, so this point will be 1 1. If it is 2, so this corner will lie at 2 2. So depending upon the value, this corner can lie anywhere on this line. But one thing is certain, in this case, this corner will always lie on this line. So why I am telling you this? Because I will be using one of these three cases in finding the PMF of Z1 is equal to maximum among X1 and X2. So now I will use all this information to calculate the CDF of Z1. So let's see how to calculate the CDF of Z1. So let's now calculate the CDF of Z1 is equal to maximum X1 comma X2. So Z1 will be equal to the greatest among X1 and X2. So let's first write down what is Z1. So Z1 will be equal to X1 under what condition? So Z1 will be equal to X1 when X1 is greater than X2, and it will be equal to X2 when it is X1 when X2 is greater than X1, and Z1 will be equal to X1 or X2 when X1 is equal to X2. So what will be the CDF? For CDF we use capital F Z1 for a sample value small z1 is nothing but the probability that z1 is less than equal to small z1. This will be x1. So let's see what will be this probability in each of these cases. So for the first case, I am writing this as case 1, this is case 2, this is case 3. So in case 1, for case 1, I am writing it as subscript 1. This probability will be z1 will be equal to x1. So x1 is less than equal to z1 when x1 is greater than x2. So this will be equal to probability that x1 is less than equal to z1, this inequality, and combining this inequality we can write it as less than capital X2. Here it is x1. So now we will understand what is the region that is covered by this inequality. This region consists of intersection of or common region of two regions. First region is the region that is this region, and second region is this region. The intersection of these two regions will be the region that is this region. So now I will draw this region x1 greater than x2. This region will lie below this x1 is equal to x2 line. This line is x1 equal to x2 line, and this region is x1 is greater than x2. So all the region that is lying below this line is the region that is covered by this line. So I am going to draw that region with red lines. So this region is the region number, this region, x1 is greater than x2. This region is x1 is greater than x2. Other region, that is this region. To draw this region, we need a sample value z1. So I'm taking the sample value z1 as this value. When x1 is this value, you can take it anywhere. This value I'm just taking to understand what is this region. You can take it here, you can take it here, anywhere you can take it on x1 axis. So now I will draw x1 is equal to z1 line. So that line is this line, parallel to x2 axis. Similarly downward. So this is x1 is equal to z1 line. So here x1 will be equal to sample value z1. So this region specifies that random variable x1 can have any value below or equal to z1. So the region that is lying on this line or to the left of this line is the region that is specified by this equation. So I'm going to draw it now. So it is this region. Whole this region is the region that is blue region is x1 is less than equal to z1. So you can take any value of x1 that is lying on the left side of this x1 is equal to z1 line or on this line. For example, I take this value. So here I take this value. For example, I take this value to be -4. Suppose z1 is 2. I am taking it for example. So this value is always, you take any value or any point in this region, in blue region. For that point, its x1 value is going to be less than equal to z1. That is the meaning of this equation. So the region that is common to this blue region and red region is the region that is this region. So I'm going to draw it with yellow lines. So it will include this x1 is equal to z1 line, this line, as well as the region to the left of this line that lies below this x1 is equal to x2 line. So this is the region that is specified by this equation. Of this whole region that I'm drawing here with yellow lines. Similarly, we can find out that for second case, I'm going to write it as subscript 2. So it is probability, we can show that it is probability that x2 is less than equal to z1 and it is greater than x1. So this is nothing but the probability. So we have taken z1 here. So on at this point it is z1 is equal, this point is z1 comma z1. So here x2 is z1. So let me draw a line here. So x2 is equal to z1 line is this line, which is parallel to x1. So this is x2 is equal to z1 line. So the region that is specified here by this equation is the region that includes this line as well as the region that lies above this x1 is equal to x2 line. So this whole region, this region is the region that is specified by this equation. I will again draw it by yellow lines. So finally I will draw the probability for the third case. So it is CDF for the third case. So it will be probability. We can see probability that we can write here x1 or x2, any, less than equal to z1 when x1 is equal to x2. What will be this? It is nothing but the probability that x1 lies on x1 is equal to x2 line. This whole is x1 is equal to x2 line, and to the left of z1 is equal to z2 line. So it is the probability that x1 lies on this x1 is equal to x2 line from this to up to infinity on this line. So this CDF, overall CDF of Z1 is nothing but the superposition of probability of these three cases, which is nothing but the probability that x1, capital X1 and x2 lie in this region. Now if we recall what we have discussed previously, that this region is similar to the region of a CDF that we learned in the definition of CDF with the corner at Z1, Z1. So this is nothing but the joint CDF of X1 and X2 with the parameters small z1 and z2. So the CDF of, I will write it here. So the CDF of z1 is nothing but the probability that x1 is less than equal to this parameter z1 and x2 is less than equal to small z2, which is nothing but the joint CDF from the definition of joint CDF of x1 and x2. Here we will write z1, which is nothing but the joint CDF of x1, x2, z1, z1. So hence we conclude that the CDF of z1 will be equal to the joint CDF of x1 and x2 with parameters z1, z1. So this is the conclusion that I wanted to bring in front of you. So this is the final result. So now we will use this to further define the CDF of Z1 in case X1 and X2 are independent. We concluded in previous discussion that the CDF of Z1 with the sample value Z1 is nothing but the joint CDF of X1 and X2 with parameters Z1, Z1. So this is nothing but the probability that X1 is less than equal to Z1 and or intersection X2 is less than equal to Z1. If this is A, X1 less than equal to Z1 is A and X2 less than equal to Z1 is B, then we know if A and B are independent, then this is equal to probability of A into probability of B, which is nothing but X1 is less than equal to Z1 into probability X2 is less than equal to Z1. This is nothing but the marginal CDF of X1 and this is the marginal CDF of X2. So this can be written as Fx1 of Z1 into Fx2 of Z1. So this is the final result for X1 and X2 are independent. So this is the final CDF. From the CDF of X1 and X2, we can find out the CDF of Z1, which is maximum of X1 and X2. We note that down when X1 and X2 are independent, the resultant CDF of Z1 is nothing but the product of two CDFs of X1 and X2. This is true in general. That is when X1 and X2 are dependent or independent. Even in the case of dependent, this is valid. We can generalize these two results for n variables. Say we have n random variables x1, x2, x2, x3 up to xn, and we want to know what will be the CDF of z is equal to maximum x1, x2 up to xn. Then we can generalize that CDF of z will be equal to the joint CDF n-dimensional joint CDF calculated at values at this sample value, where each of these is z. This is written n times. So this is valid even if x1, x2 up to xn are xi's are dependent. Xi's are dependent or dependent. In both cases, this is valid. This is valid for both dependent and independent. But if they are independent, we can simplify this further into products. So if xi, where I can vary from 1 to n, xi are independent, mutually independent. They are mutually independent. Then we can write CDF will be the products of individual will be product of individual CDF. So these two are the final conclusions. So now we will be using these results to calculate the problem that was given to us. So let's see how to use these results to calculate such problems. So it is given in question that x1 is distributed uniformly. So x1 is given that it is uniformly distributed over range -1 to 1. It is a discrete random variable. So its Pmf we can write that x1 can take these values -1, 0 and 1. For these values only, the probability that x1 is equal to some sample value small x1 is non-zero only for these three values. So its probability is 1 by 3, 1 by 3 and 1 by 3. This is called Pmf. This is called Pmf, probability mass function of x1. If z1 is maximum of x1 comma x2, we know that the CDF of z1 for a sample value z1 is equal to product of CDFs of X1 and X2 for the same sample value Z1. This we know. From our previous discussion we know this. So if I can calculate the CDF of X1 and X2 separately and then take a product of it, I can well define what will be the CDF of Z1. So firstly, for that we know we need to calculate the CDF of X1. So by the definition of CDF, the CDF of X1 will be f X1 of some sample value X1 is nothing but the probability that X1 is less than equal to that sample value X1. So this is equal to summation of all values of random variable X1 that are less than or equal to small x1. Probability X1 is equal to small x1. So this is nothing but the sum of all the probabilities of random variable X1 whose values are less than equal to small x1. If X1 is less than -1, this will be 0, because below -1 the probability is 0 for all values of X1. So sum of all such probability is 0, and for X1 is greater than equal to -1 and less than 0, here it is X1. So in this range the CDF will be equal to sum of all the probabilities that are strictly less than 0. So for less than 0, only non-zero probability is 1 by 3. So its value is 1 by 3. For next range, it will be 0 to 1. Here, the CDF will be equal to sum of all the probabilities that are strictly less than 1. So below 1, there are only 2 non-zero probabilities. So its value is 2 by 3. Next range is X1 is greater than equal to 1. It will include all the probabilities below 1. So sum of all these three probabilities will be equal to 1. So this is the CDF of X1. This CDF I have drawn in this diagram. You can note down here that here X1 is a discrete random variable. So for discrete random variable, we can note down here that its CDF is a staircase type diagram. This is true. This is not only true for this case only. Any type of discrete random variable will have its CDF, a staircase diagram, where the step size will be equal to its probability. You can see here for -1, when x1 is equal to -1, its probability is, if the step size is 1 by 3. Similarly, for when x1 is 0, here the step size is 2 by 3 minus 1 by 3. So the probability is 1 by 3. We can see it here. Similarly, in this case, its CDF is, here we can see that for x1 is equal to 1, its step size is again 1 by 3. So probability is 1 by 3. Similarly, we know that x2 is uniformly distributed discrete random variable over range -1 to 1. So similar to x1, by following the same procedure that we did here, we can calculate the CDF of x2, and I will leave its calculation to the students, and you can finally verify that its CDF will have this type of staircase type diagram. So after calculating the CDFs of both x1 and x2, next what we have to do is take the product of these two CDFs to calculate the CDF of Z1. So now we will take the product of these two CDFs of X1 and X2. We can see here that for values of X1 that are lying below -2, its CDF is 0. Similarly, for values of X2 that are lying below -2, we can see here its values are 0. So 0 multiplied by 0 will be 0. So for values of Z1 that are lying below -2, we will have a 0 valued CDF. Similarly, in range -2 to -1, from the CDF of X1, its value is 0. From the CDF of X2, in range -2 to -1, its value is 1 by 5. So 0 multiplied by 1 by 5 will be again 0. In range -1 to 0, the CDF of X1 is 1 by 3. In range -1 to 0, the CDF of X2 is 2 by 5. So 1 by 3 multiplied by 2 by 5 will be 2 by 15. Similarly, for other ranges of X1 and X2, we can multiply and get the final result, which I have already drawn here. You can verify it on your own. So this is nothing but the CDF of Z1. So now, after calculating the CDF of Z1, we can easily calculate the Pmf of Z1 from its CDF, since we know the probability is nothing but the step sizes. We can see the first step size is when Z1 is -1. So Z1 can have non-zero probability only at step sizes. So we can see the step sizes are present at -1, 0, 1 and 2. So we can have non-zero probabilities only at these values of Z1. So probabilities will be equal to the step sizes. At -1, we can see its step size value is 2 by 15. So probability is nothing but 2 by 15. At 0, its step size is 6 by 15 minus 2 by 15. So it is 4 by 15. At 1, its step size is 4 by 5 minus 6 by 15. So 4 by 5 we can write 12 by 15 minus 6 by 15 is 6 by 15, which is nothing but 2 by 5. For value 1, its step size is 15 by 15 minus 12 by 15. So it is 3 by 15, which we can write as 1 by 5. So this is the Pmf of Z1, which you can verify from the part 1 of this video that its value will be same that we have calculated here. So now we have seen both the methods of calculating the Pmf of Z1. In part 1 video solution of this question, we saw how to calculate the Pmf using Pmf method, and in this part of video we saw how to calculate the Pmf using CDF method. Now I will giving you a shortcut technique to calculate the Pmf of Z1 without using both these methods. So let's see that shortcut method. So now I will give you shortcut method to find the Pmf of Z1. Note this method is valid only if the random variable x1 and x2 are discrete random variables. For continuous random variables, if x1 and x2 are continuous random variables, this method is not valid. So let's see what's the shortcut method. It's given that x1 is uniformly distributed over -1 to 1 and x2 is uniformly distributed over -2 to 2. So we know that probability x1 is equal to x1 will be 1 by 3 for x1 equal to -1, 0 and 1, and probability x2 is equal to small x2 will be equal to 1 by 5 for x2 is equal to -2, -1, 0, 1 and 2. So in this two-dimensional x1 x2 plane, I have drawn what are the possible points that can be obtained by using x1 and x2 in an ordered pair x1 comma x2. What are the possible points? X1 can be, so different possible points can be when x1 is 1, so there are 5 possible points. One is x1 is 1 and x2 is minus 2. Other possible point is 1 and minus 1. Another possible point is 1 comma 0, 1 comma 1 and 1 comma 2. So we can see similarly for x1 is equal to 0 and similarly for x1 is equal to minus 1. We can see there are 15 possible points that we can show here in x1 x2 plane. So also we know that the joint Pmf probability x1 is equal to x1 and x2 is equal to x2 will be, since x1 and x2 are independent, so it is nothing but the product. So it will be 1 by 3 into 1 by 5. So it will be 1 by 15 for all these possible 15 points. So this is the joint Pmf of all these 15 points. So now I will directly calculate the Pmf of Z1. So the probability, let's see what will be the probability that Z1 is equal to minus 2. To see what is this probability, we draw a region here whose corner point is at minus 2 comma minus 2. So it will be this region. Since there is no point lying here on the boundary, the white boundary that I have drawn here, since there is no point lying here, so we can write it, this probability is directly 0. Similarly, let's see what is the probability that Z1 is minus 1. For this, we draw the boundary with the corner at minus 1 comma minus 1. So it will be this boundary. Since this boundary has 2 points lying on it, so this probability is nothing but the sum of the joint probabilities of the points that are lying on this boundary. So the joint probability here is 1 by 15 for this point, and similarly for this point the joint probability is 1 by 15. So sum of these two joint probability will be 2 by 15. Similarly, probability that Z2 is 0. So for that, draw a region with corner at 0 comma 0. So that boundary is nothing but the third quarter lying here. Since it has 1, 2, 3 and 4 points lying on this, so its probability is the sum of the 4 joint probabilities of these 4 points. So it is 4 by 15. Here it should be Z1. Similarly, probability that Z1 is 1. For that, draw a region with corner at 1 comma 1. So that region will be, so this boundary has 6 points lying on it. So its probability here, so this probability is nothing but the sum of joint probabilities of these 6 points. Since here for each point joint probability is 1 by 15, so the answer is 6 by 15. Similarly, we can see what is the probability that Z1 is 2. For that, we draw a region with its corner lying on 2 comma 2. Since it has 3 points lying on this region, no point is lying on this part of this section of this boundary, and only these 3 points are lying on this boundary. So this probability is nothing but the sum of joint probabilities of these 3 points. So it will be 3 by 15. For all other points, if you draw the boundaries, you will see that there are no points that are lying on the boundaries. So the corresponding probabilities are 0. These 4 are the only probabilities for which it will be non-zero. For all other points, if you draw the boundaries here and try to see what are the points lying on the boundary, so no point will be lying on such boundaries and the corresponding probabilities will be 0. So on next page we can write the Pmf of Z1. So Z1 can take these values and the corresponding probabilities will be 0, this is the same result that we obtained in the PMF method as well as the CDF method. So we can solve this type of problem by any of these 3 methods, but in exams I will suggest you to follow this shortcut method as it will save your time in exam. So now we will see the gate problem that we saw in the part 1 of this video, in which I have modified it from minimum to maximum. So let's see that problem. So this is the problem that came in GATE exam. In GATE exam, here they have asked about minimum function, but I have modified it as maximum function just for the sake of your practice. So let's see what is this problem. So in this problem, there are 2 tosses. The coin is tossed 2 times. So first toss and second toss. In first time, the output is labeled as M. So output can be 0 and 1, and the corresponding probability that capital M is equal to small m from sample value is 1 by 2 and 1 by 2. Similarly, for the second toss, the random variable is n, and corresponding outputs are 0 and 1, and the probability that capital N is equal to some sample value small n is 1 by 2 and 1 by 2. Now the second step is to write the joint PMF of M and N. To write the joint PMF of M and N, firstly we need to find out what are the ordered pairs that are possible for M and N. That is, what are the different points that are possible in M and N plane. So firstly we will see what are the different points in M and N plane. Suppose this point I am representing by small m and n. So for m is equal to 0, there are 2 possible ordered pairs. These ordered pairs are 0, 1 and m is 0 and n is also 0. Other possible ordered pairs are when m is 1. So when m is 1, here we will write m is 1 and can be 0, and other possible pair is m is 1 and n is also 1. So these 4 points we can plot in M and N plane. So if this is our M axis and this is our N axis, so this point will be this point will be 0 comma 0 point. Similarly, this point is our other point. This point is 1 comma 0 point. This point will be 0 comma 1 point, and the last point will be 1 comma 1 point, and this will lie on our m is equal to n line. So this is our m is equal to n line. So this is our m is equal to n line, and 0 0 and 1 1 will lie here. So the joint probability that m is equal to m and n is equal to n will be equal to the product of marginal probabilities, because here m and n are independent random variables. So this will be equal to, so here for all values of m it is 1 by 2. Here for all values of n it is 1 by 2. So 1 by 2 into 1 by 2 will be 1 by 4. So joint probability will be 1 by 4 for all these 4 points. So now we will calculate the PMF of x is equal to maximum m comma n. From our shortcut method, we know to calculate the probability x is equal to x, we will need to consider rectangular boundaries with corner lying at point x comma x. For this sample value, we will consider a point in mn plane whose corners are at x comma x. For example, if you consider a boundary here which is parallel to m and n axis and with corner lying here, let this point be minus 3 comma minus 3. You can see here there is no point lying on this boundary, since all the 4 points are located here. Out of these 4 points, no point is lying here. So probability that capital X is minus 3, this point is minus 3 comma minus 3. So the probability capital X is equal to minus 3 is 0. Similarly, for all such boundaries whose corner lie in this third quadrant, there will be no point out of these 4 points that will lie on that boundary. So for all such values of x, the probability will be 0. So the first non-zero probability will come when we consider this boundary, and corner will be at 0 comma 0. So for that case, probability will be, x value will be 0, because we are considering corner at 0 comma 0. So the probability will be the sum of all the joint probabilities of points that are lying on this boundary. Here only one point is lying, so only one joint probability will be considered. So that is 1 by 4. Similarly, if you draw any such boundary with corner on this axis, we can see that until the corner will be 1 1, there can never be overlapping between the boundary and the points. So this is the only case of boundary where there will be overlapping between points and the boundary. So that case will be, so this boundary will correspond to when x is 1. So this probability will be the sum of joint probabilities of these 3 points. The sum of 1 by 4 plus 1 by 4 plus 1 by 4, sum of joint probability is 3 by 4. So these are the only two cases here for which the PMF will be non-zero. For all other values of x, we can see the probabilities will be 0. So now we will calculate expectation of x. which is nothing but summation over x and probability that x is equal to small x for all values of random variable x. So it will be when x is 0, into its probability. So 0 into 1 by 4 plus x is 1 into its probability. So 1 into 3 by 4. So it will be 3 by 4. You can check it from the part 1 of this video solution that it is the same result that we obtained in previous part 1 video. So I hope you have learned a lot from both of these videos, part 1 and part 2, and you can now handle any question on maximum of M and N type questions. So I hope you will like this video and subscribe to my channel for more such videos and to learn more such concepts. So thank you for watching this video. We will meet in next video. Thank you.